Hi,
This call is now being recorded.
so welcome to the next session. Today we'll be covering regression. So earlier we had covered all these topics, including the importance of statistics in real life, center and spread of the data, probability, conditional probability, and random variables. Um, and then we covered continuous random variables, Bernoulli trials. In the next session, we covered distributions, sampling and center limit theorems, confidence intervals, and last session we talked about hypothesis testing. This session we are going to cover regression testing. Now, from the last session, these are some snapshots from the last session where we ended our discussion on the decision theory, where we saw what type 1 and type 2 errors were. Right. Now, let's start the discussion on regression. Till yet, we have done stats on one variable at a time, right? Whether it was coming from particular sampled uh, data that we had, or from a population of pill takers, right? So but in this chapter we'll see how do we relate two variables with each other, right? If you remember back when in session 1 we took an example where we were trying to plot the heights and weights of different students, of 92 students, right? And now we try to see how they are related, right? So now most of you must have gone through I mean, while back when in maths class you were building your graphs and all. So let's say if you build a graph for y is equal to x plus 2, something like that, x plus some constant variable, so this will be a linear line, right? So what this means is that if you know x, you are able to perfectly predict y. But in real life scenarios, this doesn't happen every time, because on the values of y, it may not be y may not be only dependent on x. That's why we are not able to see a relationship, a linear relationship every time in our real scenarios, right? For example, in this case, the height the height has an influence on weight, but there may be other factors as well, like the sex, age, body type, and a random some other variation. Now, let's label the weight data as y. Right, on the y-axis we have the weight, and on the x-axis we have the height. Okay, and weight data is y, so the data points are yi, and the height data is x, and so the data points are xi. Now, height and weight of the student, we plot it on a scatter plot, two-dimensional scatter plot, and this is how we see the values. Okay. Now, once we have all these numbers, we just draw some dotted lines. We calculate x mean and y mean. So let's say these dotted lines are the means of x and y. In a regression analysis, what we want to do is we want to fit a straight line uh, in the data points that we saw. We want to fit a straight line, and in that exercise, the x is called an independent variable and y is called a dependent variable, right? So your LHS, whatever variables are there in your LHS, which are x, they will be independent, and y will be dependent on response variable. You can call x as predictor variable also. This is the form of a linear regression. illustrate this process, again, we take, out of the 92 students, we further take the data only of 9 students. And let's say these are the data, okay, and they have plotted the same on a scatter plot and calculated the means of x and y for this smaller data set. Now, how do we know? How do we get the best fitting line out of this? So visually, we can see probably a line something like this, like going somewhere like this. It may be the best fitting line, but let's see. So what we want to do here is we want to minimize the spread of the y values from the original y values. Okay, so let's say this dark black line is my regression line, and these are the points, right? These are the actual points, which is xi yi. So this gap, I want to minimize this gap. Okay, and for that I use a parameter called sse, which is sum of squared errors. What it is, the formula is, it is just a summation of differences of yi and yi cap. So your yi cap are the points on the line, on the regression line, and yi are the actual values. So it's actual minus uh, the line, or you can say it predicted as well, actual minus predicted, difference of actual minus predicted squared. The sum of it is called sse, sum of squared errors, right? So the aim is to minimize this sum of squared errors. Right? Once we solve it mathematically, we will obtain that this will be minimized. So mathematically, to just to give you a brief, how we will solve it mathematically is your yi will be your yil will be some fixed value, and your yi cap will be dependent on a and b and xi. So in that case, to minimize this, you will equate the partial differential to zero. Okay, and then you will obtain the a and b values. So because your xi and yi are n-dimensional vectors, so this will be taken away, and we will have to go to n-dimensional space to do it. So that there's already possible explanations for it, but right now in this video we won't discuss that. So when we solve it, we obtain a b. The b value is equal to xi minus x bar into yi minus y bar. We will summate it and divide by xi minus x bar squared, right? And the a will be y bar minus bx bar. Right? Once we calculate b, we can calculate a as well. X bar and y bar, they are obviously the means of xi and yi. Now, we define some expressions, which is sum of squares around the means of x. Sum of squares of the means around x is xi minus x bar squared, and the sum of it across all the values of x. Similarly, we have for y as well, and the cross product is defined as xi minus x bar into yi minus y bar. So that will be ss xy, and we already know ss xx and ss yy. So we'll be using these expressions later, so that's why we are defining it. Now let's do some calculations for the rigged data. You can try this on your own, but this is how it will be. We have the xi's and the yi's. Then we can obtain the x bar and the y bar. Now, since we have x bar, we can obtain the xi minus x bar. We can obtain yi minus y bar. we can obtain these values as well, and we can also obtain the SSXY, right? You can try it. So what it will give is the B value will be 1200 by 240, right? Uh, so it will be 5 and A value will be minus 200. So if you substitute those values, you will get a line which is minus 200 plus 5x. And if you plot that line, you will get this graph. Okay. So these dots are the actual values, and this is the fitted line. Also, your fitted line, this will always pass through x bar and y bar, which are your means. Okay. Now we introduce another term called ANOVA, analysis of variance. And now we have one question: if it's a good fit, how good is it? Right? We want to answer this question because all the points that we see are missed, right? So we want to know how bad is it? How bad is it missing the values, or how good is the fit? Now the fitness, the goodness of the fitness depends on how sloppily the data points are spread out, okay, or how far the data points are spread out, how many data points are there. So the goodness depends on that. So basically, how big the SSE is, right, related to the total spread of the data. Now, possible scenarios can be this scenario in which it's a very good fit. We have a small standard squared errors, sorry, sum of squared errors, and even compared with small total spread, right? Uh, the total spread that we have is very small in this one, in the first example. In the next example, we have a bad fit. We have big sum of squared errors. Yes, this will definitely be big, but relative to small total spread. So the total spread is not too much. This is limited. So it's not. So the error is relative, right? Uh, Total spread is smaller basically. In the third one, it's also a good fit. So we have a large spread, right? But the SSE is not that big. And in the last one, we have a large spread, and we have a large SSE as well. So it's a bad fit. Now, let's quantify the variability in Y. Okay. Once we have predicted Y based on the values, based on the values of xi and yi, the mean values of xi and yi. Let's say I have predicted some yi cap, then I need to quantify it. I need to explain the variability in y. Okay, so what we do is, let's say these are your regression lines. These are your mean lines. Okay, y bar, and the difference, this line, this difference between mean and your predicted value is regression, and the error is your predicted minus actual, or actual minus predicted, whatever it is. So yi are the predicted weights, right? Yi cap are the predicted weights, which are already determined by the regression line. So this component is regression, this is error. We prepare the ANOVA table in which we have the source of variability, we have the formula, and we have the values for the sample data that we have. So if we measure the regression, the source of variability, let's call it, we call it regression, and the formula for that is yi cap minus y bar squared. Sum of all of it is the SSR. And similarly, we have the error component as well, yi minus yi cap squared, the sum of it, and the total is obviously yi minus y bar squared. sum of all of it, right? So naturally, we can see that SYY that we calculated earlier, which is YI minus Y bar, this one, right? So this is equal to SSR plus SSE, right? I mean, we can't make sense from this formula, but yeah, it's true. Statistically, when we look at it, right, it will come out to be true. Now, uh, for the data that we had, in which the regression line we obtained y is equal to minus 200 plus 5x, these are all the calculations. In this, SSR is 6000 and SSC is 4426. Now, this SSR that we calculated, the source of variability here is a regression. So, this gives me the total variability due to regression, right? That is prediction, our prediction. Now, SSC, we have already seen what is SSC. We note that the SSC should be relative to something, right? So, this SSC divided by SSYY, which is, uh, your yi minus y bar squared, sum of it. So, that this proportion is a very important proportion, which is called the squared correlation. Or we can also see this will be equal to 1 minus SSE upon SSYY, right? So this is the correlation coefficient, or R squared. We call it R squared as well. We call it correlation, squared correlation as well, right? Not the correlation coefficient, my bad, but squared correlation. Um, we can see from here that R square will always be less than 1, and the closer it is to 1, meaning SSE is lesser, so your curve fit is very good, right? And if it's tighter, or the closer it is to 1, the tighter the fit is, right? R square is equal to 1 will correspond to a perfect fit. If you calculate R squared for the data set that we had, we obtain an R squared of 0.58, right? So what this R squared means? This R squared means that 58% of the variation in weights is explained by the height, because we were regressing weight on height, right? The other 42% is error, right? 58% we can explain with weight, with height, but rest 42 will be error. That is what it means. Also, we look at the correlation coefficient, which is just the square root of R squared, right? And the sign of correlation coefficient will be the sign of B only, right? So we have R is equal to sign of B into under root R squared. R squared will definitely be 1, right? But your R correlation coefficient can not always be positive. It can be positive as well, it can be negative as well. It takes up the sign of B, which is the slope of the curve, of the fitted curve line. So now you can see that negative R would mean that you have negatively related x and y, right? So, or a negative slope. Some examples of correlation coefficients with one, so that's a linear line with minus 0 point line, that should be a negative slope. For R is equal to 0, I mean, basically where you have no correlation, or you don't see any particular fit, you don't see any merit in it, and R is equal to zero point 0.7, right? Okay, so let me take you through an example, a working example. Okay, so here what we have is, so row number from row number 4, you will see that we have 1000 values of x. Sorry, not 1000, we have 100 values of x, and we have 100 corresponding values of y, which we call xi and yi. So they are both plotted on this graph, right? The blue ones are the xi and yi's, right? Now, I calculate the sum of squared errors of, sum of squared errors of xx, which is xi minus x mean squared, and again y minus y mean squared. Then I calculate xi minus x mean into yi minus y mean, which is ss xy. So based on all of these, I will get a b and a value. So my b value would be ssxx upon ssxy, and a will be utilizing the b and the means, right? Once I have them, I will have the predicted values or the regression line, which is this a red line. So now you can see that when we had all these points, we were able, so regression helps us to get the best possible line, which is, having the least amount of errors with all of its points, right? So, so this red line is the linear regression line. Now, we calculate the SSR as well, the variability as well, right? The regression component, which is y cap minus y mean squared, the sum of it, and the sum of square of errors, right? Which is yi minus y cap squared, the sum of it. So when we have calculated both of them, we calculate the r squared, which is 0.78, and the correlation coefficient, uh, or the coefficient of regression, sorry, which is 0.89, right? So this r squared 0.78 is a very good value, and obviously this means that r is 0.89. It's plus 0.89 because my slope or b is 1.86, which is positive. So r will also be positive. So yeah. Also, if you see here, right, if you try to change the values of b, let's say if you want to make it 3, no, you can't make it 3. Let's make it 1. So if we make it 1, this goes beyond your coefficient of regression. It becomes 0.48 and your squared decreases, right? So, you can try with other acceptable values of b, not some values of b like 3, because then it would not make sense, right? Your r, it should never be greater than 1. All the acceptable values of p, if you try with them, you will see that the maximum r squared that you get is 0.78, and it will be based on the value, based on the formulas that we have seen. Coming back to the slides. Now let's see what is the statistical inference in this analysis, right? Up till this point, we have been doing data analysis, and we were describing the nearest linear relationship between x and y. Now let's take a step back, and we want to look at it from another lens, and we will regard these 92 students as a sample of the population of students at large, right? So let's see what we can infer. A regression model for the whole population is going to be of this form: y is equal to alpha plus beta x plus epsilon, where epsilon is the error term, y is the dependent random variable, x is independent variable, right? Alpha and beta, they are the unknown parameters. We want to estimate these. And epsilon, it represents the random error fluctuations. This is the regression model for the whole population. Now, for the example that we saw, the height versus weight model, Y is the weight, X is the height. Alpha and beta are unknown, right? And we can think of X as the random components of weights of Y, right? And they will be different for different values of X, which is the height. The distribution of epsilon, it will be different for different values of X, right? What they're seeing is 5 footers, they may vary less in their height than the 6 footers. Now, we make a simplifying assumption. Let's suppose that the variation is same for all of them, and we have the mean as zero for all of them. The mean should be zero, right? And the epsilon should be independent and normal. So, if they are independent and normal, the mean should be zero, and we assume that the standard deviation for all of them is same. This is the simplified ones. So now, what do we want to say is the earlier obtained values were this one, right? So the weight model, it might be y is equal to minus 125 plus 4x plus epsilon. Now epsilon is going to be normal with mu is equal to 0, right? And sigma is equal to 15 pounds. Then what this model says is if the students who are, let's say, 76 inches, so their distribution will be we put 76 into this equation, and what we get is y is equal to 175 plus epsilon. So what it means is that if x is equal to 76, if um if my x is equal to 76, y will be 175. Right? If the height of the student is 76, the weight is normal with mean 175 and standard deviation of 15 pounds. Right? So this is what we can infer from here. So let's say this was the mean value, and the confidence, I mean the standard deviation is 15. So 68% you're confident that the value will be between these numbers. So this brings me to the end of the first part of regression. I think I'll be discussing more on the the inferences that we can take from the normal from the regression analysis. I hope it was informative. Thank you.